Have you seen a balance like this before? When each side of the balance has an equal mass, the balance is, well, balanced. In math, equations are kind of like balances, because the equal sign in an equation tells us that the values on each side are equal to one another. This is true not only with numbers, but with equations involving variables too. So when we have an equation like x plus 10 equals 16, we know that the left side, x plus 10, must have the same value as the right side, 16. We can use this fact to help us figure out the value of the variable x. So how do we do that? Well, there are a few important steps we follow to solve an equation like this one. First, we need to isolate the variable by using the inverse operation. Isolating the variable means getting it by itself on one side of the equation. Right now, the variable is on the left side of the equation and it's not isolated because 10 is being added to it. To isolate the variable, we need to use the inverse operation. Inverse operations are opposite operations, which means they undo each other. For instance, the inverse of addition is subtraction. If we start with a number like 0, add 10, and then subtract 10, we would still just have 0. So subtracting 10 cancels out or undoes adding 10. Let's apply that to our equation x plus 10 equals 16. Don't forget, we want to isolate the variable by using the inverse operation. Since 10 is being added to x, we need to use the inverse operation, subtraction, and subtract 10 from x. Adding 10 and subtracting 10 cancel each other out, giving us x plus 0 on the left side of the equation, which we can write as just x since adding 0 to anything doesn't change its value. Uh-oh, do you remember how earlier in the video we learned that an equation is like a balance, so both sides must be equal? To keep the equation balanced, we need to do the same operation on both sides of the equation. So if we subtract 10 from the left side of the equation, we also need to subtract 10 from the right side. 16 minus 10 equals 6, so now we have x on the left side of the equation and 6 on the right side of the equation. This means x equals 6. Of course, it's always a great idea to substitute the value we get for the variable into the original equation to see if our solution makes sense. If we substitute 6 for x, we have 6 plus 10 equals 16. Since the sum of 6 and 10 is 16, that means both sides have a value of 16 when x is 6, so x equals 6 is the solution to this equation. Let's try solving some more one-step equations together, starting with 42 equals z minus 25. Now, you might be noticing that this time the variable is on the right side of the equation. But don't worry, we can use the same steps. First, we need to isolate the variable by using the inverse operation. In this equation, 25 is being subtracted from z. The inverse of subtraction is addition, so to isolate z, we need to add 25 to z. Since subtracting 25 and adding 25 cancel each other out, this leaves us with just z on the right side of the equation. Then, to keep both sides of the equation equal, we also need to add 25 to 42. 42 plus 25 is 67, so 67 equals z. Before we move on to the next problem, let's make sure our solution is correct by plugging in 67 for z in the original equation. Since the difference of 67 and 25 is 42, that means both sides have a value of 42 when z is 67. So 67 equals z is the solution to this equation. Let's solve this equation next. 100y equals 500. Are you thinking this equation looks a bit different too? Even though this is a multiplication equation, because 100y means 100 times y, we still need to solve it by isolating the variable using the inverse operation. Can you guess what the inverse of multiplication is? I bet you already knew that division is the inverse of multiplication. So, because our variable y is being multiplied by 100, we'll need to divide it by 100 to isolate it. Since division undoes multiplication, the 100s on the left side of the equation cancel each other out, leaving us with y. We can't forget to divide the right side of the equation by 100 too. 500 divided by 100 is 5, so y equals 5. As always, let's plug in 5 for y in the original equation to see if it's correct. The product of 100 and 5 is 500, which means both sides have a value of 500 when y is 5. So y equals 5 is the solution to this equation. Do you know how to solve for m in this equation? Since m is being divided by 20, we'll need to use the inverse operation and multiply both sides of the equation by 20 to isolate the variable. Since multiplication undoes division, the 20s on the left side of the equation cancel each other out, leaving us with m. On the right side of the equation, we have negative 12 times 20. Remember, when we multiply integers with different signs, the product is negative. That means negative 12 times 20 is negative 240, so m equals negative 240. I bet you already know the last step. We need to plug in negative 240 for m in the original equation. The quotient of negative 240 and 20 is negative 12, so m equals negative 240 is the solution to this equation. Alright, let's solve one final equation together before you go. Negative 195 equals a plus negative 87. To isolate the variable, we need to subtract negative 87 from both sides since negative 87 is being added to a. The negative 87s on the right side of the equation cancel each other out since adding negative 87 and subtracting negative 87 are inverse operations. That leaves us with just a on the right side. On the left side of the equation, we have negative 195 minus negative 87. Subtracting a negative is the same as adding its opposite, so we can think about this problem as negative 195 plus 87. Negative 195 plus 87 is negative 108, so negative 108 equals a. And of course, if we plug in negative 108 for a in the original equation, we have negative 195 equals negative 108 plus negative 87. Since the sum of negative 108 and negative 87 is negative 195, we know a equals negative 108 is the solution to this equation. Wow, you just solved one-step equations involving adding, subtracting, multiplying, and dividing. So I'm confident you've got the steps down now.